Introduction. Today's a holiday and we shall go to the market for shopping in the evening. Tani, please bring me a glass of cold water.
Sure, Father. Father, your glass of water.
Thanks, Tani.
Father, I want to ask you something.
Yes, sure.
How does a refrigerator work? How does it make cooling inside?
Refrigerator is an application of thermodynamics. It pumps out the heat from inside to outside.
Okay, Father, I got my answer. Can you tell me more about thermodynamics?
Let's study more about thermodynamics. Objectives. At the end of this lesson, you will be able to define thermodynamics, know thermal equilibrium, define laws of thermodynamics, define heat, internal energy and work, calculate specific heat capacity, analyze thermodynamic state variable and equation of state, understand thermodynamic process, analyze heat engine, refrigerator and heat pump, define reversible and irreversible process, understand Carnot engine. Definition. Thermodynamics is a branch of physics which deals with the concepts of heat and temperature and the interconversion of heat and other forms of energy. Thermodynamics is a macroscopic science. It deals with the bulk systems and does not go into the molecular constitution of matter. Refrigerator, room heater, sweating water bottle, windshield misting are some common daily life examples of thermodynamics. Thermal equilibrium. Thermal equilibrium is the state of a system in which the macroscopic variables that characterize this system do not change in time. Let us take an example. In winter season, when you open the door of your house, then the heat moves out of the house. To balance out the temperature, after few minutes, you feel that the temperature inside and outside the house is same. This is due to the thermal equilibrium. Thermal equilibrium depends on the surrounding and the nature of the wall that separates this system from the surrounding. Zeroth law of thermodynamics. Zeroth law of thermodynamics states, if two systems A and B are separately in thermal equilibrium with a third system C, then the system A and B are in thermal equilibrium with each other. The physical quantity which determines whether or not a system is in thermal equilibrium with another system is called temperature. Now, Zeroth law can also be stated as, there exists a scalar quantity called temperature, which is a property of all the thermodynamic system such that equality of temperature is a necessary and sufficient condition for thermal equilibrium. Internal energy, heat and work. The amount of energy that a body has within itself due to random motion of its molecules and their interaction is called internal energy. The energy that flows from one body to another due to the difference in their temperature is known as heat energy. The energy transferred by the system to another that is accounted for by changes in the external generalized mechanical constraints on the system is known as work. Let's take an example. A gas is kept in a container. At the top of the gas, piston is mounted. The container is heating up from the bottom. Now, gas molecules are in random motion due to their internal energy. Heat energy given to the gas molecules raises the temperature and they expand. When molecules expand, then a large volume is covered. This displacement is the work done. First law of thermodynamics. The internal energy U of a system can change through two modes of energy transfer, heat and work. First law of thermodynamics states that the energy delta Q supplied to the system partially increases the internal energy of system delta U and rest to do the work on the environment delta W. Delta Q is equal to delta U plus delta W, where delta Q is equal to heat supplied to the system by the surroundings. Delta W is equal to work done by the system on the surroundings. Delta U is equal to change in internal energy of the system. If heat supplied to the system is used up entirely by the system in doing work on the environment, then delta U is equal to 0. It gives delta Q is equal to delta W. Specific heat capacity. The specific heat of a substance is the amount of heat required to raise the temperature of a unit mass of the substance through 1 Kelvin or 1 degree Celsius. The heat delta Q required to increase the temperature of mass m of solid by an amount delta T is given by delta Q is equal to mc delta T. Molar specific heat is given by C is equal to 1 by N into dQ by dt. Nearly the same amount of heat, 25 joule mole inverse Celsius inverse, is required per molecule to raise the temperature of each metal by a given amount. Variation of specific heat of solids with temperature is shown in the given graph. The specific heat of water as a function of temperature from 0 degrees to 100 degrees Celsius has been plotted. Example. Let's take an example. How many meters can a man climb with energy from a slice of bread which produces 100,000 calories of heat? Man having weight 60 kg. Assume that the human body works at an efficiency of 28%. Take the average value of G to be 9.8 meter per second square. Let's see the solution. Here, mass and efficiency is given, which are 60 kg and 28% respectively. Let h be the required height in meters. Now, we know that the work done is equal to potential energy. So, by simplifying it, we get 60 into 9.8 into h joule. By calculating it, we get 586 h per 4.2 joule. Heat associated with the process is equal to 100,000 calories. On evaluating, we get 28 by 100 into 100,000, which is equal to 588 h upon 4.2. So, h is equal to 200 meters. Hence, the man can climb 200 meters. Thermodynamic state variable and equation of state. When a system is in thermal equilibrium with its surroundings, then the pressure P, volume V, and temperature T of the system describes the thermodynamic state of the system. They are also known as state variables. Equation of state is the relation between P, V, and T satisfied by a substance. The simplest equation of state is the ideal gas equation. When we plot a graph between pressure and volume for a particular temperature, curve obtained is called an isothermal. Plot of different isothermals for CO2 is given in this graph. Thermodynamic process. Quasi-static process. The system which changes its variables so slowly that it remains in thermal and mechanical equilibrium with its surrounding throughout. In a quasi-static process, at every stage, the difference in the pressure and temperature of the system and surrounding is very small. Isochoric process. In an isochoric process, volume is constant. No work is done on or by the gas. The heat absorbed by the gas goes entirely to change its internal energy and its temperature. The change in temperature for a given amount of heat is determined by the specific heat of the gas at constant volume. Isobaric process. In an isobaric process, pressure is fixed. The heat absorbed goes partly to increase internal energy and partly to do work. The change in temperature for a given amount of heat is determined by the specific heat of the gas at constant pressure. Cyclic process. In a cyclic process, the system returns to its initial state, since internal energy is a state variable. Delta U is equal to 0 for a cyclic process. The total heat absorbed equals the work done by the system. Isothermal and adiabatic process. Isothermal process. In this process, temperature of the system remains constant. For a given number of moles of an ideal gas, we have PV is equal to nRT, where N is equal to number of moles, T is equal to temperature of gas, R is equal to universal gas constant. Since T is constant, therefore PV is also constant. The essential condition of isothermal process are: temperature should remain constant. Changes must take place at a slow rate. Specific heat of the gas is infinite. Adiabatic process. In this process, there is no exchange of heat between the system and the surroundings. Delta Q is equal to 0. The essential conditions of adiabatic process are: there should be no transfer of heat energy. Changes must take place at very fast rate. Specific heat is 0. The pressure-volume curves of an ideal gas show two adiabatic process connecting two isotherms. Heat engines. A heat engine is a device which converts a portion of heat extracted from a reservoir at a high temperature into useful work done and rejects the balance to a reservoir at a lower temperature. Heat engines consists of four components. Source: 1. From where heat is extracted. Sink: 1. Where a part of heat is rejected. Working substance: some gas or vapor which expands to do some useful work. Machine: a mechanical system on which useful work is done. Efficiency: the efficiency of a heat engine is given by the ratio of work done to the heat extracted from the source. Efficiency is equal to 1 minus Q2 by Q1. Refrigerator and heat pump. In a refrigerator, heat energy flows from the cold reservoir to the hot reservoir. It absorbs Q2 amount of heat from the cold reservoir at T2, has work W done on it by an outside agency, and rejects Q1 amount of heat at hot reservoir at T1. The system is run by an outside energy source. Coefficient of performance of refrigerator is given by alpha is equal to Q2 upon Q1 minus Q2. Second law of thermodynamics. The first law of thermodynamics suffer from following limitations. Number 1. It does not indicate the temperature in which change can proceed. Number 2. The first law of thermodynamics gives no idea about the extent to which the changes takes place. Second law of thermodynamics concerns with the direction in which energy transformation naturally takes place. The two well-known statements of second law are: Clausius statement. It is impossible to construct a device which, when it operates in a cycle, produces no effect other than the transfer of heat from a colder to a hotter body. Kevin-Planck statement. It is impossible to construct a device which, when it operates in a cycle, extracts heat from a source and converts it wholly into work. Reversible and irreversible processes. Reversible process. It is the process which can be retraced in the opposite direction so that the system and the surroundings pass through exactly the same state at each stage as in the direct process. Electrolysis, slow compression or extensions of a spring are example of reversible process. Irreversible process. It is a process which is not exactly reversed. The system does not pass through the same intermediate state as in the direct process. All chemical reactions and natural process are example of irreversible process. Carnot engine. The Carnot's engine works in reversible cycle known as Carnot's cycle. A Carnot's cycle has following steps. Isothermal expansion. The cylinder is placed in thermal contact with the source and weights over the piston are gradually reduced. The gas expands isothermally at a constant temperature T1 and volume increases V1 to V2. The amount of heat absorbed during this expansion is Q1. Adiabatic expansion. The cylinder is placed on the non-conducting stand and weights over the pistons are further reduced. The adiabatic expansion is carried till the temperature falls to the temperature T2 of the sink. The volume of the gas increased from V2 to V3 and its temperature falls from T1 to T2. Isothermal compression. The cylinder is placed on the sink and weights over the piston are increased very slowly. The gas compresses isothermally at T2 and its volume reduces to V4 from V3. During isothermal compression of heat rejected to sink BQ2. Adiabatic compression. The cylinder is placed over the non-conducting stand and weight is further increased. The adiabatic compression is carried till the temperature of the gas rises to the temperature of source. Thus, the volume of the gas decreases further from V4 to V1 and its temperature rises from T2 to T1. In a Carnot cycle, efficiency is given by Q1 by Q2 is equal to T1 by T2. Did you know? Clausius showed that everything really happens because energy moves from areas of high energy to areas of low energy, from hot areas to cold areas. Energy cannot be reused once it has turned to heat and dissipated, just as you cannot rebuild an igloo once the snow has melted. The second law of thermodynamics says that energy is dissipated every time it is used, so the entropy of the universe must increase. Summary. Let us summarize what we have learned. Thermodynamics is the branch of physics that deals with the concepts of heat and temperature and the interconversion of heat and other forms of energy. Thermal equilibrium is the state of a system in which the macroscopic variables that characterize the system do not change in time. If two systems A and B are separately in thermal equilibrium with a third system C, then the systems A and B are in thermal equilibrium with each other. The energy supplied to the system goes in partly to increase the internal energy of the system and the rest in work on the environment. The specific heat of a substance is the amount of heat required to raise the temperature of a unit mass of the substance through 1 Kelvin or 1 degree Celsius. It is impossible to construct a device which, when it operates in a cycle, produces no effect other than the transfer of heat from a colder to a hotter body. It is impossible to construct a device which, when it operates in a cycle, extracts heat from a source and converts it wholly into work.